Okay, today's lecture is on something called the composition of functions. So before we do that, I'm going to go ahead and just describe it in my own words a little bit. So I'm going to insert a blank page. And what composition of function means is we're going to use the output of one function as the x value for the input of another function. So let's say that I was going to do the composition of the function of f with g of x. Now notice that normally we would write something like f of x, but in place of the x, I have g of x. So what that means is I'm going to find the value of g at x, and then I'm going to take that and I'm going to dump that into f of x. So it's kind of like saying, okay, here's g of x, here's f of x, and when I do the composition of those two, I'm going to take this function and use it as the input for the other function. So if I had numbers, here's an example how that would work. Let's say I had f of x is equal to x squared, and let's say that g of x was equal to x plus 1. And let's say I wanted to set x equal to 3. Okay, so what this would do, if I would have f of g of x, here's one way to look at it, that I could take the 3 and substitute it into the x for g. That would give me 4. So g of x would be equal to 4. And then it says use that input into f of x. So I would take the 4 and put it into the x squared, giving me a 16. So I'm using the output of one function as the input of another. Now, what we don't want to do is we don't want to do this evaluation, find the answer, and then substitute it into f. We want to do that substitution all together. So, for example, if I would have the composition of f with g of x, and let's just use these two numbers again. So I said, okay, f of x is equal to x squared, and g of x was equal to x plus 1. What I could do is I could take this x plus 1 and put it in as the x in the f of x squared. So what I would get is I would get f of g of x is equal to x plus 1 squared, which of course would be x squared plus 2x plus 1. So that's what I'm doing. I'm taking the output of g, using it as the input of f. Okay, and note the way it's shown here. So I'm going to show a couple other methods the way they write it. So, for example, if I wanted to put f into g into f, I could say this. Okay, that's saying the composition of g into f, the composition of f with g. Another way to do it could be use this little degree sign and write it like this. So that just means the same thing. This is the way maybe your book does it. And another way to do it could have been something like this, right? Some of them may show it like that. And that's not fog, that's a little bitty circle there. Okay? So with that, let's go to what the notes say. Well, I don't know where this page is. I'll have to delete it later. Oh, it's at the start. Okay, so let's go to what the notes say. Okay, the nomenclature, it says, here's one way to do it. I'm creating a new function, h of x, which is the composition of f of x with g of x. So I'm putting g of x in as the input to f of x. Another way to do it is use the little circle like I said. Another way to show it could simply maybe be like this, or the book may have it. All those things kind of mean the same thing. Now, what we have to be aware of is this is not commutative. Putting g into f will give you a different answer than if I put g into f of x. So what I could say here is f is not necessarily equal to putting f into g. Sometimes they may be, most of the times they won't. So you cannot switch the order. So putting F into G is not necessarily the same as putting G into F. And oh, I said that there, number 3. And to find the domain of F, of a composition of functions, what you're going to do is you're going to find, since G of X, I'm putting G of X into F, I'm going to find the domain of G of X, and then I'm going to find the domain of G of X when it's substituted into F of X. And we'll see how that works in just a second. Okay, so let's go to a couple examples. So the first example I have is I have F is equal to 3x to the minus 1. G of X is equal to 2x to the minus 1. And what I want to do is I want to do the composition of F with G of X. So I'm putting G of X into F of X. So what you can see is in place of the X, I took this whole G of X and I put it into that X. Now, if there were more X's, I would have to put G of X into every X in F of X, every one of them. So anyway, when I work this out, I'm going to take the 2x to the minus 1. Since it has a negative 1 exponent, it's going to drop down to denominator position, and it's going to look like that. Okay, so that is the composition of F and G of X right there. And let's talk about the domain. Okay, the domain of G, what I start with right here, it's 2x minus 1. So 2x minus 1, right up here, I could put any number in for x. So the domain of G of X is all real numbers. Now, when I put G of X into F, when I actually do the composition, you can see that I have this thing right here. And what we can't have is, you know, that the denominator can't be 0. So we need to find whatever value of x is going to make this denominator equal to 0. So I could just set up, say, okay, I can't have this. That can't occur. So 2x is equal to 1, x is equal to 1/2. If I put a value of 1/2 into the denominator, it goes to 0. So I can't have x equal to 1/2. So my domain would be all real numbers, because that was what we had as the domain of G of X, except x equal to 1/2, because that makes the denominator go to 0. And if I wanted to write that in interval notation, how I could write that is I would say, okay, x could be anything all the way up to 1/2. Now, I'm not going to use a closed bracket because that says it could equal 1/2, and it can't. So we use an open bracket, and we say, okay, that's the union. That means combined with all the values of x going from 1/2 to positive infinity. So that would be the interval notation to saying all real numbers except the 1/2. Okay, let's go to another one. Okay, here's another composition of functions, and let's take a look and see what it's telling us to do. It's telling us to put the function f into itself. So if I'm going to do that, here's my 3. So if I look at the original equation, I'm going to have a 3. And then I'm going to have the x value, and whatever the x is going to be to the negative 1. And what I'm going to do is into that x value for f, I'm going to plug f into that. So inside of that parentheses, I'm going to have 3. Well, what the heck? I'm going to have 3x to the minus 1. Okay? So now let's go ahead and see what that's going to be when I write it out. So what that's going to be is that's going to be 3. Hold on. I better explain this. Okay, let's go back real quick and just take a look at what the domain of f is. So the domain of f is actually equal to 3 over x. So if we take a look at the domain of f, that's going to have to be equal to x is all real numbers except x cannot equal to 0. So all real numbers except x not equal to 0. Okay, so I wanted to go ahead and put that up there. Now let's go ahead and work this problem out. So if I have 3, and I'm going to distribute the negative 1 in, that's going to be times 3 to the negative 1, and x to the negative 1 times the negative 1 would be x. All right, so that's going to be equal to 3 to the 1 minus negative 1, gives me 3 to the 0, x. And of course, anything to the 0 power is 1, so I get x. So the function, the composition of function f with itself gives me x as an answer. But however, that when we look at to figure out what we're going to do with the domain, we can't look at the simplified part. What we have to look at is what we started with originally. And you can see that what I have originally is because I would have f of x in the denominator position, or even the way f of x was as it started is I could not have x equal to 0. So even though when I substitute f into itself, when I simplify it, it's equal to x, the domain of that has to be what it looks like when I start the problem. And so the domain of this is still going to be domain would be where x, all real numbers where x is not equal to 0. Okay, let's do another example. So what we're going to do is we're going to do the composition of g with f of x. So I'm going to put f, the function f, into all the x's that I have in g of x. Okay, so here is g of x up here. Let's just write them up there so we can see them a little better. G of x is equal to 2x minus 1. F of x is equal to 3x to the minus 1. So if I put g of x into f of x, that's going to look like this. So this, let's go ahead and rewrite x just so we can see how it's going to look. F of x is equal to 3 over, we move the x down to the denominator. So if I put this value right here, which is f, into all the x's of g, what I would get is 2. And now I have 3 over x for that x, minus 1, which would be 6 all over x minus 1. So there's my composition right there. So if it tells me to evaluate it for some value of x, I would plug that value of x in right there. So for example, if it told me to evaluate it at x equal to 6, what I would do is I'd say, okay, g of f evaluated at 6. So notice I'm saying I'm evaluating at f at 6 and using that input for g. Then what that could be is that would be, I'd put 6 in, 6 all over 6 minus 1. That would be 1 minus 1. So it would evaluate to 0 if I put x equal to 6 in there. Okay? Now what we have to do is remember we have to look at the domain of f of x, whatever that is it starts with, and the domain of what the function g of x has in it. So the domain of f, we already said that at the beginning, that the domain of f, because f is up here, we said the domain of f is x not equal to 0, because f was, remember, 3 over x. We couldn't have 0 as a denominator. And when I look at, after I put f into g, I still have x as a denominator, so the domain of f substitute into g would also be x, all real numbers where x is not equal to 0. So the intersection of those would be, the domain would be all real numbers where x is not equal to 0. Okay, let's look at another example. So what we have here is we have f of x is defined as 4 over x to the minus 5th. So I'm going to write that as 4 all over x to the 5th. And g of x is x to the 3/4. So we could think of that as the 4th root of x cubed, just so we can think about the domains a little better. So we'll talk about the domains in just a second. Let's go ahead and evaluate this. So what it says is for all the x's in G, I'm going to put the value of f of x in there. And f of x is 4 over x to the 5th. And I'm going to use, so what that would look like if I substituted that in is G is x to the 3/4. So I would have into that x, I would put 4x to the 5th, the 4th root of that, then I'm going to cube it. Okay, now I'm not going to work it out that way, but that's what it would look like. And let me just make sure I got that right. We said G is x to the 3/4, which is the 4th root of x, and x is actually 4 over x to the -5th. So I wanted to put it like that so we could actually get a look and see what my domain would be. Okay? All right, so let's go ahead and combine G and f of x using rational exponents. So what I'm going to have is G of x, so I've got x to the 3/4, and I'm going to put into this x 4x to the -5th. So I have 4x to the -5th, and that is going to go into G, which is x to the 3/4. So I'm taking out the x here, and I'm plugging in the whole 4x to the -5th. So this would be the composition of G with f of x. Okay, so let's go ahead and work that out. That's going to be distributing in the 3/4. It'd be 4 to the 3/4. And then if I take the x to the -5, I would get x to the -15/4, which I could also think of as 4 to the 3/4 all over x to the 15/4. Okay, and that would be the composition of those two. That would be my equation. Now to figure out the domains, what I could do is I'm going to look at the domain. I'm substituting f of x into g of x, so I'm going to look at the domain of f of x. So the domain of f, and let's look and see what f was at the start. F was 4 over x to the 5th root, right? So the only thing that could make that f become 0 would be, because the x to the 5th is in the denominator, would be if x is equal to 0. Okay, so what I could say here is for f, we have x not equal to 0. Now let's look at what I have after I combine them. So the domain where they're combined, well, I have an x in the denominator position, but that x is also a 4th root. So I can't have any values where the square root is going, because it's an even root, so you can't have any values where the root would have a negative number under the root, right? And you also can't have this x be equal to 0. So the domain of my final answer is going to be all real numbers where x is greater than or equal to 0, because it can't be negative and it can't have a 0 in the denominator. I guess I must have made a mistake when I said it. This is the domain, so it's all values of x that are greater than 0. I can't equal to 0 and I can't have a negative.